Hi, we are the radar remote sensing team, and today we will be talking about the applications of Sentinel-1 SAR data on flood analysis.
Here's a quick introduction to our team. Hi, my name is Salsabeel Eldeeb, and I'm from Ormond Beach, Florida.
Hi, my name is Iris Moo, and I'm from Bloomfield Hills, Michigan.
Hi, I'm Rohan Puppala from Alpharetta, Georgia.
Hello, my name is Luke Short and I'm from Providence, Rhode Island.
Hi, my name is Sophie Wassef and I'm from Napa, California.
Hi, my name is Kelly Zhang, and I'm from Pasadena, California.
And our mentor, Dr. Chen.
For background information, we are going to compare two different methods of remote sensing and explain which one is better for our purposes of flood detection. The first method is optical imagery, which relies on sunlight deflecting off the Earth's surface to be captured by a satellite's sensors. The sensors detect light in various wavelengths, but typically it's visible light. Sometimes it can be infrared light as well. And analyzing the intensity and the patterns in this deflected light is a pretty straightforward way to create clear color and bird's eye view satellite images of our Earth's terrain. So here's just a helpful visual graphic of optical imagery. The clear band behind the satellite shows the terrain that has already received light waves from. And the center image, which is a really clean image, is the type of picture that you would expect to be produced by optical sensing. So overall, as a tool, optical imagery is very useful. The only problem with it is that because of its reliance on sunlight, it can't function during night or when there are clouds or fog. And so on the right, that's an example of the type of image that would be produced when there's cloud cover, which can be pretty annoying when you're trying to visualize a flood that's on the ground.
Now we'd like to talk about data collection using SAR. So what is it? SAR stands for Synthetic Aperture Radar, and its main purpose is producing high-resolution images of Earth's terrain and geographical features. Satellites use their active sensors in order to collect quantitative information. First is phase, which is the distance or displacement in the reflected wave. Next is amplitude, which is the intensity of the reflected signal. And finally, we measure the time interval as well. In this image, you can see a satellite following its flight path, directing a radar beam at a point called pixel A. The line of sight is the direct path that the signal will follow when going from Earth's surface back to the satellite. Over here, we can also see two outputs produced by this process. First is the amplitude information, which gives us information about our terrain, like rocks, ridges, or sloped areas. Furthermore, we can also see that the phase information displays small displacements as colorful patterns. Both of these measurements allow SAR data to be extremely detailed down to the millimeter and produce maps that showcase Earth's deformation.
While optical imagery's raw form may be easier to understand, its data spectrum is greatly limited because it's only functional during certain light and weather conditions. On the other hand, radar's active sensors provide exact measurements of the Earth's surface during all conditions. For our purposes, radar imagery was the clear choice. We use the Sentinel-1 satellite for our SAR data. Sentinel-1 offers global coverage every 6 to 12 days. Its radar operates on a C-band frequency, which falls between the X and the L band pictured below. It has multiple polarizations, which means it can transmit and receive signals on different planes, and, most importantly, it's open source, which makes it great for all levels of scientific investigation.
While optical imagery offers clear visuals, its weather limitations make SAR more reliable for consistent data collection. This leads us to our research question. How effective is SAR data in detecting and mapping floods? Now, let's look at our rationale.
So first is addressing gaps in existing flood maps. Current flood risk maps, like those created by FEMA and other agencies, often underdetect the frequency and full extent of floods. These underestimations can leave flood-prone communities vulnerable and underprepared. By using SAR imagery, we hope to highlight where current flood maps fall short, as well as demonstrate how SAR-based methods can be more timely, consistent, and accurate for flood detection on the global scale. Next is promoting open, accessible, and cost-effective tools. While spaceborne SAR data like Sentinel-1 is technically open source, it remains difficult to use without specialized skills and tools. Our project aims to bridge this gap by developing a flood detection algorithm that is not only effective but also easy to use for the public. This increases global accessibility to real-time flooding, especially for underserved or disaster-prone regions with limited resources. And finally is rethinking the role of airborne flood detection. In our current time, there has been an increased interest in airborne storage systems from private companies. They're often deployed for high-resolution, immediate flood mapping, but they're expensive, slow to mobilize, and limited in coverage. With the growing capabilities of spaceborne SAR missions like Sentinel-1 and upcoming platforms like NASA's NISAR, this project investigates whether space-based approaches alone can provide sufficiently accurate flood maps.
So the first thing we did was experiment with Google Earth Engine, which is a platform that provides access to a large archive of SAR satellite imagery, and it allows users to analyze data on a wide range of Earth terrain. So when attempting to visualize flooding on Google Earth Engine, we first have to set our study location, either by inputting geographical coordinates or just drawing our own area in over the Earth map. Then we have to choose a before time range and an after time range. Google Earth Engine compares the satellite images in the before range and the after range to determine where the terrain actually changed between those two times. Next, we have to determine our parameter values. Difference threshold is what we use to control how much the amplitude of a pixel has to change between the two set dates to be considered flooding. The pass direction is the orientation in which the satellite passes our target area. The options for this are ascending or descending. Polarization options are VH and VV. VH means that the received signal was horizontally polarized, while VV means vertically polarized. And VH is generally preferred when doing flood mapping because it is better at detecting smaller changes in the terrain. After determining all of our parameters and running the program, Google Earth Engine produces a few different layers, including the before flood, the after flood, the difference layer, and the flooded areas. The before flood layer shows the terrain from the before date that we set, while the after flood layer shows the terrain from the after date that we set. The difference layer has pixels whose color reflects the change in amplitude between the before layer and the after layer. A lighter pixel means that there was more change between those two layers, while a darker pixel means that there was less change. The difference layer is the driving force behind the flooded areas layer, which is a mask that shows blue pixels in all the places that experienced an amplitude change that was greater than our set difference threshold.
So here we're showing our Google Earth Engine flood detection results over Dhaka, Bangladesh. On the left is the before flooding SAR image collected from December 2019 to March 2020, which is during Dhaka's dry season. You can see the urban areas are relatively bright, while the surrounding landscape is fairly dark, indicating low backscatter, likely due to drier conditions. In the middle is the after flooding image from late June to early July of 2020 during the monsoon season. This image shows visibly darker regions, especially around rivers and low-lying zones, indicating increased surface water. On the right is the flood prediction map, generated using a difference threshold of 1.22. Areas detected as flooded are highlighted in blue. Clearly, the areas that got darker by visual inspection match with the blue detected on the flood map. In Madera County, we tested Google Earth Engine using two different time periods. One was during the dry season in 2017 and one during a known flood period from 2016 to early 2017. Surprisingly, the dry season detection of the left shows more flooded than the actual flood period on the right, even though we used the same exact threshold of 1.45. This mismatch suggests that GEE's flood mapping isn't reliably capturing real-world flood events here, likely due to land cover, agriculture activity, or backscatter noise. While Google Earth Engine is a powerful tool, we encountered several key limitations during our flood detection analysis. First, flash floods are hard to capture. You need to select very precise dates or you risk missing the event entirely. Second, because GE is a shared cloud platform, high user traffic can cause runtime delays or even timeout errors during larger processing tasks. Third, threshold selection is difficult without ground truth data. As we saw in Madera, inaccurate thresholds can lead to widespread false positives, especially when speckled detections appear in areas far from known water bodies. Together, these challenges motivated us to move beyond GE and develop a more reliable custom flood detection approach using raw SAR data.
Here are the steps we took to map and detect flooding using SAR data. All SAR data is stored in binary, so before we could do anything else, we had to read in our files and convert the binary data into actual amplitude and phase measurements in the form of a complex matrix.
Next up, we created a time series. By visualizing SAR images over a large time frame, like 1 year in our case, we were able to validate our flood predictions. By analyzing water pixels across various test cases, we determined an average amplitude that would serve as a threshold. This step is crucial in determining the validity of our program, as we needed to make sure that it can differentiate between permanent water, like lakes, rivers, and ponds, versus temporary water, like flooding.
To isolate the flood, we first set the threshold to detect areas with a drop in backscatter and find connected regions larger than 30 pixels, which we then consider floods. For visualization, we use a white and blue color map, white for background, and then blue for flooded pixels. We then loop through each image, calculating the amplitude difference from the average and using that to isolate the flood. To build a flood frequency map, we sum up binary flood mass over time, then converting it into a percentage. Areas flooded in over 90% of images are marked in dark blue, and a duotone map highlights these zones in blue and makes everything else white. Gaussian smoothing is then applied to clean up the edges and make flood-prone areas appear more visually clear.
Now that you've seen the steps we went through to process the data and what models we chose to focus on, we'll walk you through our results case by case. Dhaka, located in Bangladesh, was our first case study. It's the perfect candidate due to its distinct wet and dry seasons and because of the severity of flooding in the region. It's particularly prone to flooding because of its annual monsoons, low elevation, and proximity to a lot of rivers.
These are SAR images over the Meghna River and Dhaka created MATLAB, so the left image shows conditions on January 11th of 2023, and the middle image shows the same region on July 10th of also the same year. Darker areas indicate lower backscatter, often being connected to water, and on the right we see the average amplitude across 29 images, which serves as a baseline for detecting changes. Notice here how the flooded regions in July appear significantly darker compared to both the baseline and the dry season image, corresponding with it being the monsoon season of Dhaka.
This time series animation of Dhaka shows flooding over time, where darker areas indicate increased surface water. Around June and July, the peak of the monsoon season, you can clearly see flooding intensify, confirming that the SAR data captures seasonal flood patterns accurately.
These two images show how radar backscatter amplitude on specific dates differs from the long-term average. On the left, January 11th shows relatively minor deviations, indicating pretty stable surface conditions. On the right, July 10th shows a much stronger variation, especially in blue areas where amplitude drops below average, and this suggests widespread surface changes from the seasonal flooding.
And now for our water mass, which we have derived using two steps. First, using the average amplitude threshold determined earlier, we classified pixels into water. Then we only plotted those water pixels that were there at least 90% of the time, so we would avoid temporary flooding. This validated both our Python and MATLAB code and proved that they were working correctly. Next is our water frequency map, which calculates the amount of time or the probability that a water pixel has been there throughout. And the darker pixels indicate the permanent water, while the lighter blue tones indicate water that's only occasionally there. What makes this map especially useful is its ability to quantify surface water persistence. Instead of being a binary representation of just water or no water, it shows a probabilistic insight, leading us to be able to see how each area was affected. And this actually adds nuance to flood risk analysis, as we can see how different parts of the city could possibly be impacted. Using this information, city governments can make informed decisions and be able to provide the resources and safety measures to those who need it most.
These two binary maps show where flooding is along the Meghna River while masking permanent water and other land cover. On January 11th, during the dry season, there's only scattered patches of flooding appearing, which could be caused by false positives, by image noise, or surface roughness. In contrast, on July 10th, widespread and dense flooding is visible, consistent with the monsoon rainfall.
Our next focus is Madera County, California, which is located in the Central Valley and poses as our rule case study. Flooding typically occurs from November to April due to storm surges, heavy rainfall, and snowmelt, though there is no distinct flood season. Due to the flat elevation of the region, water tends to spread quickly and widely, making agricultural regions sensitive to flood impacts. The San Joaquin River is located west of the county and is the prime water body in that area. Overall, flooding in this area diminishes crop production and local community life.
These SAR images of Madera County compare April 7th near the end of wet season with July 24th during the dry season. The lake in the upper right remains dark in both images, showing how water consistently has low backscatter. In July, other dark patches appear, for example in the bottom left corner, but this is from bare land having lower reflectance in contrast to its surroundings, not an actual water body. The April image is overall less bright, suggesting more widespread surface moisture at the end of the rainy season, since water and saturated soils reflect less radar energy. These maps show radar amplitude patterns over Madera County using 30 satellite imageries from 2023. The left image shows the average amplitude, with brighter areas reflecting consistently strong backscatter, like buildings or rough terrain. The right image maps amplitude variance, highlighting how much each pixel's value fluctuates over time. High variance, seen in bright spots, often corresponds to consistently changing areas, like irrigated fields, urban cities, or surface water changes, while stable regions, such as bare land or water bodies, appear darker. To better observe the San Joaquin River, which appears quite small in the full Madera County SAR images, we use Google Earth Pro to identify reference points and find a focused boundary around the river. The geographic coordinates were converted to image row and column indices in MATLAB to crop the region, and the clearest imagery, which is shown on the right, came from averaging 30 SAR images, highlighting how SAR is statistical, which means that stacking images will reduce noise and make surface features more distinct.
Jefferson Parish, Louisiana is our final case study. This region has no defined flood season due to the frequency of flood events throughout the year, which have two main causes: storm surges during the hurricane season and heavy rainfall. This region is highly susceptible to severe flooding due to its low elevation and subsidence. The first two figures you see here have been produced by taking the average amplitude of all SAR data from the years 2016 and 2022. Upon first inspection, you may not see much change between the two figures, but by taking a closer look in the bottom part of the figures, which are the coastal wetlands, you may notice that the 2022 year has a significantly darker pixels. We took a closer look at the data by focusing in on these regions. Here, darker pixels signify greater water body and degradation of coastal wetlands. This progression, seen in these tube figures, is important to map because the coastal wetlands protect Jefferson Parish from natural disasters. This finding, using SAR data, shows us how SAR can help us improve future predictions of flooding. Here, you see a fixed amplitude mask, where water pixels are bright and land pixels are dark. In the future, we hope to improve this model to see how floods progress throughout the year.
This project demonstrated efficiency of utilizing Sentinel-1 data in Python and Google Earth Engine in order to map floods across environments. The most successful region was Dhaka, Bangladesh, where distinct monsoon seasons aligned with the SAR's ability to capture changes. While Jefferson Parish posed slightly more challenges due to its mix of elevation and land types, such as urban and coastal. The region also had no pronounced dry and wet season, yet the distinct water bodies still allowed for accurate and reliable flood mapping.
Madera County was our most difficult case as it primarily consisted of short flash flooding. This means that Sentinel-1 might actually miss this short event because of its 6 to 12 day pass range. And also the land was a mix of both rural and urban landscape, which made it harder and more inconsistent to analyze. A lot of the land was also marked as permanent water, which led to false positives.
SAR data is very useful. It enabled us to detect floods and flooding patterns, but it does have some limitations. Sentinel-1 takes 12 days to return to an area. If that area has a flash flood the day after Sentinel-1 passes, the flood will likely be gone by the time the satellite returns, so we'd be missing out on some crucial data. Another problem is that in some cases, farmland will have a detected amplitude that is higher than water's amplitude, making it hard to determine what is water and what is land. This is what complicated the Madera County case. But it isn't just farmland that can interfere with results. When vegetation grows on top of a river or lake, SAR struggles to detect where there is water. The image on the right is a picture of Jefferson Parish, which has a large swamp area. When the swamp overflows, much of the water is still covered by plants, which makes it difficult to detect flooding.
Accurate flood maps are crucial in natural disaster responses. In order to prioritize which areas are in dire needs, these maps can be used to determine how resources are distributed. It allows for improved evacuation. In developing states such as Bangladesh, infrastructure is limited, meaning reliable data allows for quicker response time. For flood monitoring, SAR imagery creates consistent data with accurate results, which allow for tracking flood growth and relations with bodies of water. Governments and agencies may use data to analyze the frequency of floods as well. In Jefferson Parish, where there is a complex blend of urban land and wetland, this is beneficial. Identifying flood-prone areas through SAR analysis allows for further interpretation regarding infrastructure development and land use. Planning ahead of time can allow urban planners to avoid high-risk zones. Moreover, less dense areas such as Madera County may leverage this approach to mitigate crop and agricultural loss. In the long run, this allows for more prominent and resistant communities when approaching floods. For our future research, we identified 3 key areas to improve and expand this project. First, algorithm development. We aim to develop a machine learning-based algorithm that can detect floods by utilizing user input, reducing the manual, complex processing needed. Second, comparison. We plan to compare our flood mapping results to existing tools like FEMA's flood maps to evaluate accuracy across different platforms. And finally, real-time monitoring. A long-term goal is to achieve real-time flood detection, ideally within days of an event, to help support faster disaster response. These steps aim to enhance both the accuracy and the practical application of SAR data for floods.
We want to appreciate our mentor Dr. Chen and her PhD students Cameron Defabry and Zijian and the SEAS program as a whole.
Thank you.
Our team would like to share some of the key takeaways we gained from the SEAS program. For me personally, I really enjoyed the speakers who would come up and talk to us about their work. I was able to learn about so many different types of science and learn through so many diverse perspectives. I really appreciated how they were able to interact with us and actually answer all of our questions. This was always one of the highlights of my day.
SEAS was a one-of-a-kind experience with amazing people. This program showed me that there are infinite ways to help others through the aerospace field, and it inspired me to find my own ways to contribute in the future. Though I am sad to go, I'm super excited to take all of the skills and memories I have gained through SEAS in my life moving forward.
I am super grateful for the SEAS experience, especially for our daily afternoon team meetings with our mentor and her PhD students, because it gave us so many opportunities to experiment with different ways of addressing the research question, all the while growing our skills and curiosity for this field of study.
I didn't come to the SEAS program with one very specific interest in mind, like aerospace engineering. I just knew that overall I really liked STEM. What's great about SEAS is that they emphasize that space science is a really broad topic that requires different people from various professions to all come together. SEAS helped me understand that no matter what academic path I head down, I can still be involved in humanity's exciting progression through space.
I really enjoyed the on-site experience and being able to expand my knowledge on the incredible work done behind the scenes at NASA. This experience was a once-in-a-lifetime. Not only did I have the chance to collaborate and bond with an amazing team and mentor, but I also heard from inspiring panel speakers who offered invaluable insight on the future of space exploration. One of the highlights was visiting the Johnson Space Center, where I saw firsthand the dedication driving NASA's mission. I'm so grateful to have been a part of this unforgettable opportunity. Thank you, C's.
At SEAS, I was able to experience working on radar remote sensing using Sentinel-1 SAR data to detect flooding. I'm grateful I got to work with PhD students and my NASA mentor who treated us like real collaborators, not just interns. But what stuck with me most was how easy it was to stay up late working on code and other things with people I'd just met, and that's because we all genuinely cared about the science.